people are still coming in, but I think maybe we start with the introduction here. So this is the second keynote of our conference. I'm really happy to be able to welcome Joelle Pineau. Joelle is a professor at the computer science at McGill University. She is also a member of MILA, the Montreal Institute of Learning Algorithms. But she also has a second job, actually two second jobs, right? She is a co-managing director of Facebook AI research worldwide, and also the director of the lab here in Montreal. And so that is a kind of a juggling between these two things, but I'm really happy to have her at a colleague at McGill. So she is an expert in machine learning and reinforcement learning, and she has received several awards and honors for her work. She's a William Dawson Scholar at McGill University. She has received the E.W.R. Stacy Memorial Fellowship. She's a fellow of the AAAI. She's a senior fellow of the Canadian Institute of Advanced Learning, and she's a member of the College of New Scholars, Artists, and Scientists of the Royal Society of Canada. And she won the Governor's Innovation Award last year. She has also been the past president of the International Machine Learning Society. So very active in many different areas. Her research spans from more theory, algorithms, to applying machine learning techniques in various settings such as robotics and healthcare. I remember very well the wheelchair that was floating around on campus. And so what she will be talking about is, I think, quite interesting also for our community. She will talk about reliability, reproducibility, and robustness. Obviously, this is a concern for all research communities, including ours. And of course, her talk will focus on machine learning, in particular reinforcement learning, and these three R's in machine learning. And with that, I'm happy to give it to Joelle.
Thank you very much, Bettina, and thank you to your committee and community for the invitation. Let me just share my screen to get us started. We should be good to go. It's a pleasure to be here with you this afternoon, for those of you in Europe, and share some of the work that we've been doing. This is work that I've mostly done with colleagues and students at McGill University over a few years. I will say it's a research direction which we did not initially intend to follow. We were focused on pursuing a research agenda in reinforcement learning and developing novel algorithms in this area. But through the course of that, the issues of reproducibility, robustness, became very pressing in some of our work, and that has taken us on a detour for a few years on these issues across the field of machine learning. And so I will share with you a little bit of what we found in this journey. And in particular, I think all of you have noticed, I'm sure, that we've had a big rise of activity research, but also applications of machine learning, deep learning, more specifically, over the last few years. And in that movement, in that trend, one thing we've observed is really the field of machine learning moving from being a quite theoretical mathematical science to being much more an empirical science. And as we've moved to this more empirical work, we've had to really stop, pause, and really question the ways in which we're engaging with the scientific questions. And so as part of my work on reproducibility, I'm very interested in establishing the right structures, the standards, the best practice that can help guide the field towards producing consistent, high quality empirical findings. And so I'll be sharing with you some of these findings. Most of what I will describe is in the field of reinforcement learning, which is my particular expertise. But I do think a lot of the findings we've seen in reinforcement learning actually apply quite readily to other fields of investigation across computer science. And so you may be wondering, what is the thread that is really running through these three R's: reproducibility, reusability, robustness? And I think this quote from an NSF report in 2015 probably explains it better than I could. Namely, this notion that reproducibility refers to the ability of a researcher to duplicate the results of a prior study using the same materials as were used by the original investigator. And perhaps most importantly, reproducibility is a minimum necessary condition for finding to be believable and informative. And so that's essentially my program for this morning, to share with you how we can explore aspects of these properties as they pertain to the scientific findings in our field. I'm, of course, not the first one to notice that there's an issue of reproducibility. A lot of this has been said across the field of sciences recently. In 2016, the journal Nature ran an interesting study surveying 1,500 plus researchers across several different fields, asking them whether there was a reproducibility crisis in their field of scientific research. And out of this, 52% said there's a significant crisis, another 38% said there's a slight crisis. And so clearly some big awareness of this issue across several researchers. Now, if you break down the results a little bit more carefully, something interesting comes up, and namely, you know, we asked them, or the survey asked them, have you failed to reproduce an experiment, either one of your own experiment or someone else's experiment? And what we see is that, you know, this reproducibility issue is touching all of them. In the chemistry, you know, over 80% of them failed to reproduce someone else's result, and over 60 of them failed to reproduce their own results. Now, computer science as a field doesn't quite show up here as an independent line. We can assume that in some sense, we have it a little bit easier than these other fields, in the sense that the materials, remember my initial definition, right? You're reproducing the work with the same materials. So the materials we use, these computers, are in fact designed to be highly reproducible machines. You expect that once you run the code and you run the code again, you should be getting reliable results. Much less variance than if your fundamental materials are, you know, biological materials and so on. And so we should have a bit of an advantage, but nonetheless, we found some of our work that it's very much an issue. It's almost like this notion of methodology certainly goes beyond just the basic materials that we're using. There are many reasons to be concerned about this at this particular point in time. I have already, you know, I think shared with you the fact that we've moved from a theoretical science to an empirical science, but also perhaps much more than that, there's really the fact that we're seeing a lot of the research and the technology move very, very quickly from the labs to the real world. Whereas in the past in other sciences, you would see maybe a 10, even 20-year delay between the invention and when it was commercialized. That commercialization time was long. There was a lot of time to sort of verify the impact of and the robustness of the results. What we're seeing with AI is a much shorter time from creation to commercialization, sometimes on the order of just a few months, 2 or 3 months. You know, new algorithm gets developed, a few months later, it's actually running in the product. Those products are reaching millions, if not hundreds of millions of people every day. And so there is a responsibility to ensure that the results that we are sharing with the community actually have a very high level of reliability and robustness, and that we have the evidence that we need to support the claims that you're making. And it's not just in the area of transportation that we're seeing this. There's a lot of changes also, of course, in the area of communication. Many of you have probably either by voice or through a typed interface interacted with a bot. And while the conversation with these agents, whether it's Siri, Echo, some of their siblings and so on, can be frustrating, it is quickly improving. The technology is improving. In fact, we're seeing these algorithms permeating almost all aspects of our digital lives. And so a lot of the decisions about what information you share, what information you receive, and how that information is treated is mediated by machine learning algorithms. And so just to share with you sort of the high level of responsibility that I expect our field to take on as we develop these algorithms. I'm assuming that most of you in this community are familiar with at least the basics of artificial intelligence. I've looked at some of the contributions of your community, and there certainly seems to be quite a bit of work on the application of AI and machine learning being used throughout the community. And so, you know, just to briefly give you an overview, while the field of AI as a whole has evolved over the last 60 years or so, really the subfield that has become the dominant paradigm is that of machine learning. And so most of the work I'll be describing today is really with respect to this area of machine learning. One of the reasons we've seen this rise of machine learning, and I don't expect that to slow down in the next few years, is really parallel by the rise in the availability of data. And so this is just a quick glimpse into the amount of data that is estimated to be available, produced by humans at this point. As you'll see, the unit on this is zettabytes, which is 1 billion terabytes. So large amounts of data in different categories being produced. And really the promise of machine learning is to be able to take advantage of this data to extract value from this data. And I do mean value in a broad sense, not just economical, but also societal value, to enable us to make better predictions and down the line, better decisions. This rise in the availability of data of different types has been happening in parallel with a rise in the availability of computation platforms. I'll point out first that this graph is actually on an exponential scale. So if you look at the y-axis, please notice that. Each of the points on this graph represents a different machine learning model that's been released in the research community. These are research models, not necessarily production level models, but it gives you an idea over the last few years of what's been the rise. And this ends just a little bit before where we are today. And just in the last few months, we've started seeing models trained with billions of parameters, 10 billions of parameters, and then moving towards 100 billions of parameters that are being trained right now. Most of these recent ones are language models. So you're seeing here a little bit at the top right, the neural machine translation, neural architecture search. What we're seeing, if this graph was, you know, up to date from the last month or two, you'd be seeing models on pre-trained language models of the type of like BERT and so on that have been released recently. So very quick consumption of computation power to be able to analyze these very large data set. And I will have to maybe come back another day and talk to you about some of the environmental footprint of this work in machine learning. I think that is a major consideration for our field. I'm not going to get into it today, but I think there's a lot of concerns and work to be done in this area also. I'll just mention it briefly today. So I've shown you sort of three major trends, one in terms of rise of data, the other one, the rise in terms of the computation. Let me show you what it means very concretely in terms of what we can do with these algorithms. And I will talk very little of algorithms today. That's not really the main message. But those algorithms that are consuming that data and running on these machines, here's an example of what they can do. This is a computer vision algorithm. 2012 was a turning point for the field of computer vision in terms of our ability to use machine learning to analyze the content of images. In 2012, we could take an image of this type and associate globally the image with a few labels of the dominant objects in the image. So in this case, it would label with people, with trees. 3 years later, through work such as faster RCNN, but other works also, you were able not just to analyze the image and tell what were the dominant objects, but you were actually able to obtain a bounding box along these objects. So this doesn't just tell us that there's people, it actually tells us where the people are, and it's able to identify with high reliability several objects in one image. 2015, we were mostly picking out objects as boxes. By 2017, we could have contour of objects at the pixel level. So what we call segmentation of the objects in the image, much more precise. It gives us the segmentation, and it also gives us the label. So if you have very good eyes or you're blowing up the sides, you see that I'm not just picking up the person, but I'm also picking up their backpack and their cup in the front bottom. This was mostly effective for objects on the foreground. We weren't really understanding objects on the background. wait just a little bit more, 2019, and now we have segmentation at the pixel level of the whole image, from the objects in the foreground to the objects in the background. And so this gives you a sense of, in the span of 70 years, how we've gone from understanding information just in an image, and the speed at which this technology is getting developed. And the example I give you here is really based on images, but we've seen in parallel similar progress with speech recognition, with natural language processing, as well as in some domains with understanding of other types of data, for example, 3D data and so on. And so with this really quick rise in machine learning, there's usually a few phases to how the work is done. You know, usually you get the data, and once you get the data, you clean up and prepare and manipulate this data. And so the data I was showing you before is drawn from a standardized images. The number of pixels is always the same. The cropping is always quite regular, and it feeds the data that has been sanitized in this way into the machine. Once you've gotten your data, you've cleaned it up, you train your model. Once you've trained your model, you use some additional data. Usually you keep out a separate test set to evaluate how well your model is doing. And step number 5, improve, may involve refinement of any of the steps. So you may decide that you need to get different data, or you need to clean up and prepare your data differently, maybe train your model differently, or actually apply a different criteria for the evaluation. And so it's actually, though I'm showing it as somewhat linear here, it's actually often an iterative process that happens over this pipeline. And so throughout all of these steps, going back to this question of machine learning as an empirical science, throughout all of these steps, there are many choices, design choices that are made of how the data will be acquired, cleaned up, how the model will be designed and trained, and so forth. Let me add very quickly, I said I wasn't going to talk a lot about models and algorithms, but I want to give you just a quick taste of what this looks like. This is a ResNet, which is one of the classical architectures nowadays for doing machine learning of the type of results that I showed you. As you see, there are many, many layers. Each of these little boxes actually represents several neurons in a very large neural network. And so one of the things you're seeing is also the type of design choices that are applied, right? Between the colors, the purple, the green, the red, there's actually different numbers of neurons that are being used. There are different types of connections. You're seeing these skip connections going at the top in some of the layers. So this is what we call the residual layers at the top. In the middle, we don't have residual layers. So in the algorithm themselves, the algorithms include many, many design choices of how the data will be processed. And so all of these different decisions along the way correspond to sources of experimental variation. And so I've listed just a few here. I could have had the page covered with different ones, but these are ones that we consider being key in how we design the process. And without having clear specification of all of these individual decisions, it is very hard to ensure that the work that you're doing is actually reproducible. And so this is one of the things that I like to call attention to, is just the space of design decisions that are happening when you're doing either machine learning research or deploying that technology in the real world. The space of these decisions that are having an influence on the results, and therefore that need to be carefully considered and documented as part of the scientific process. Let me go back to the theme of this morning's discussion. Reproducibility in particular make a difference between the notion of reproducibility and replicability, which is perhaps sometimes not clear to everyone. So the terms, I'll be honest with you, have not been used consistently in the literature. So the definition I'd share with you today is that of the American Statistical Association. But there are other sources in the literature you'll find that use slightly different definitions of this. So for the purposes of today, if you'll bear with me, we'll assume that reproducibility says that a study is reproducible if you can take the original data and the computer code used to analyze the data and reproduce all the numerical findings from the study. So it may sound like a very trivial task, but actually, as you'll see in some of the results I'll share with you, it's actually not that easy to achieve, even what seems like a very bare bones standard for scientific reproducibility. Replicability, on the other hand, assumes the repetition of the entire study independent of the original, including recollecting the data and re-implementing the code. So in some sense, that's sort of a higher bar on the process. And I will talk mostly about the easy case reproducibility today. And as you'll see, we still have some work to do even on the simple case, though long-term, what we should be aiming for is, of course, the higher standards of replicability. Allow me for a minute to tell you about the field of reinforcement learning, where I have spent sort of 20 years of my research career developing new algorithms before I got interested in this issue of reproducibility. For those of you who are not familiar with reinforcement learning, I don't require a lot of background knowledge. Let me just share with you sort of the key insight. It's a particular discipline of machine learning where the goal is to actually train an agent in a dynamic system. So as opposed to the computer vision case I gave you before, where an image comes and a decision is made from that static image, in this case, I have an agent, a robot, a computer that is having interactions with a dynamic systems. So that agent, instead of making a label, it picks an action. That action has an effect on the environment, and it receives feedback in the form of new observations, which I'm calling the state, as well as a reward signal. And the reward signal is essentially an indicator of how good the action was for that particular state of the environment. The concept of reinforcement learning stems back to the early days of behavioral psychology, back to the work of Pavlov and Skinner and some of these early researchers, which conceived of this concept for humans and animals. The idea being that you could train an agent, whether a child, a pet, you could train the behavior of that agent and shape how they act by presenting a combination of rewards and punishments. And so those of you who have perhaps had the pleasure of raising young children have probably used that at some stage. The idea of reinforcement learning in the context of machine learning is to codify this practice through a set of mathematical models and computer algorithms, and essentially try to train our agents with the same set of principles. Of course, our computer agents are less sensitive to the usual rewards of childhood. I can't really bribe my robot with ice cream. And so in this case, the reward function is actually encoded as a function, and a human has to specify what that function is. So in this particular case I'm showing here, if you had a little robot mouse running around a maze, the function would specify that finding the cheese corresponds to high reward, and exiting the maze without having found the cheese corresponds to no reward. The field of reinforcement learning has been active. The basic mathematical models were defined in the late 1950s. A lot of the work on the learning algorithms happened in the late 1980s. We've seen results in the last 5 years or so really showing impressive ability to use this framework to build computer systems that could win at complicated games. Particular system called AlphaGo was able to solve essentially the game of Go to a degree sufficient to best the best human players. Go is known for many years to be perhaps the most complicated of games due to the space of different actions that had to be considered in the branching factor of the game. And not far after that, a system called Libratus, that later rebaptized as Pluribus, was shown to be able to play the game of poker at the level of a human, again, using reinforcement learning to train through trial and error and rewards. In this case, of course, reward corresponding to monetary gains in the game, showing that you could use reinforcement learning to learn a strategy, an action strategy in poker that beats the best humans. And some of you out there may care a lot about Go and about poker, but there are many, many more applications of reinforcement learning that we are finding across several fields. What I'm showing here is just a quick taste of it across many different applications where reinforcement learning has been applied to derive better decision and action policies. In my own work, I've done several projects using reinforcement learning to enable better decision-making in medical systems and healthcare. One particular such system is the development of a control strategy for a neurostimulation device. So we have a little device that's implanted, and there's an electrode that delivers electrical stimulation to the brain with the goal of stopping seizures in individuals with epilepsy. So in that case, the action is whether to stimulate or not, when to stimulate. And the reward, of course, is higher reward when seizures are stopped or aborted. The state in this case is actually described by recording electrodes that are in real time, actually capturing the signal of neural activity in the brain. The work we did in this area was done in an in vitro model of epilepsy. We haven't moved to the phase of doing this on humans. And so we have a slice model where we can put in electrodes, both stimulating electrodes, recording electrodes, link it physically, literally to like a, computer science laptop that goes in and drives the electrode in real time to try to stop the seizures in this animal model of epilepsy. As you can imagine from this kind of case, the amount of data we can afford to get is very small compared to the amount, the graph I showed you with the zettabytes of data. These kinds of experiments are sitting at the bottom left corner, right in the corner where you're getting at best a few hundred, maybe a few thousand examples, certainly not more than that to train your system. So it's not a case of big data. But it is a case where having reproducible results is absolutely crucial. Anything that I do in the lab, I want to have high confidence on the results if I'm going to be sharing this information with clinical colleagues treating patients with epilepsy. And so this is a bit of a big gap. The domains where we've seen large success of reinforcement learning in the literature have mostly come from simulation environments. You can simulate the game of Go. We can simulate little agents walking around or playing games of Atari. When you're trying to apply reinforcement learning in the real world, you have access to much less data, much less ability to test and experiment repetitively on the same materials. And so that's really causing a lot more challenge. And it's requiring a much higher degree of reliability from the literature. I want to be able to know that when I read a finding in the literature, I can trust and have confidence in that finding before I take it out to these important problems. And so just to give you a taste of the literature in reinforcement learning over the last 30 years or so, there's been a huge increase on the number of papers coming out. If you compare, early 2000, a few, maybe 2,000 papers or so coming out a year. 2019, which is the last year showed here, over 20,000 papers published in this area. The challenge being that when you're trying to solve a new case, you're trying to crack a new application of reinforcement learning, what you have to consider is the area under the curve here and kind of look through that massive literature and try to find the method that seems the most promising for your problem. And so this is really a difficult issue if you assume that the papers don't all use reliable methodology in reporting their results. And so one of the particular area we dug into a little bit more in trying to solve our problem is, amongst this huge literature, all these papers, we narrowed it down to a set of papers that were using policy gradient methods. So in this case, very, very briefly, we have a neural network that is analyzing the state of the system. So for our neurostimulation device, in comes the information from the recording electrodes. Neural network analyzes that information and then recommends an action. So it gives a probability of each action, and then you pick the action with the highest probability. And this is kind of the canonical version, but there's a lot of variants on this idea that have been proposed in the literature. And these are baselines that are often used in the many, many papers I showed you to compare a new algorithm against a baseline. Sort of there's a core set of baselines that are very common in the literature in the recent years. And so in our own work, we started trying to benchmark these baselines to see, could we understand how well they were performing on a set of different tasks before we went in and applied them to a real world domain. So we started this benchmarking with this little domain called the half cheetah from the Mujoko suite of environments. Called a half cheetah because kind of like a cheetah the animal, you cut it in two, you just give it 2 legs. It has to learn to run. So the actions here are the angle on the joints of that little agent. And we compared the 4 algorithms, and what we saw doesn't really matter which algorithm is which. If you just look at these results of training reinforcement learning for this cheetah, you see that the red algorithms seem to be outperforming the others. That seems an interesting finding. We carry that out to 2 other domains with similar characteristics. There's a hopper environment, there's a swimmer environment. They're all kind of in the same simulation family of Mujoko. And what you're seeing is on the Hopper environment, the red algorithm suddenly gets much worse, and the blue algorithms, which was the worst one on half cheetah, becomes the best one. And on swimmer, blue is still best, but now it has a huge difference, variance in terms of its performance, and red is still performing very poorly. Now, this is a bit difficult to understand what to do, because based on these experiments, I have 3 domains which are relatively similar to each other, and yet the conclusions I'm drawing from comparing these algorithms are not consistent. And so if I need to pick one algorithm to go and use for neurostimulation or some other important control problem, it's hard to know from these results which one is the best one. And so we pursued our investigation a bit further. All of these algorithms, because they're standard in the field and they have open source code, we were using somebody else's code. So we thought maybe we don't have the right implementation for one of these algorithms. So we went back, found other implementations. GitHub is a wonderful source of machine learning algorithm these days. Wonderful, maybe, you know, with an asterisk in this case. What we found is for 3 different implementation of this TRPO, one of the flavors of policy gradient, we were seeing a lot of variance between the results. And this should be the same algorithm applied on the same data. Remember my definition of reproducibility. We thought maybe just TRPO was very difficult to implement. People are getting all sorts of results. We tried the same thing with DDPG, one of the other flavors of policy gradient algorithm. Same kind of thing. The difference between the different code bases was very large, showing significance of results where there should not have been any significant difference in the results. We started digging into why. Remember, I gave you a list of all the possible sources of variations. So we started varying the network structure. So how many layers in my neural network, how many neurons? We see that that does explain a large part of the variance. We also started changing the activation. So in each of these neural networks, there's a mathematical function that applies the nonlinearity. We saw some difference related to this. We started modifying a few other parameters, the scaling of the reward, the normalization transform applied at each layer of the neural net. Again, a lot of difference coming, a lot of experimental variation coming from any of these design choices. And so one of the difficult issue here is when you're comparing many different algorithms, perhaps trying to propose one new approach, it's not always the case that you're motivated to find the best hyperparameter for each of these baseline. And I think for your community where many of you are doing applications of machine learning, you may not be re-implementing each of these algorithms every time. You may be using some of these libraries that are now open source and publicly available. And this is perhaps a word of caution to look very carefully at what are the default values that come with these libraries and that you can't reliably apply them blindly, because you will see a very high variance in your results if you don't do so carefully. In our case, you know, we were trying to do fair comparison. We gave each of the algorithms same amount of data, same amount of computation, and you see the result that we got. We went a little bit further, and I, you know, was sort of work over several weeks with my students. One week they came back and they said, you know, Joelle, we found something that looks very interesting. Have a look at this result. So they start by presenting this graph, and I say, okay, that seems to be a pretty clear trend. And in each of these lines, they had completely retrained the pipeline 5 different times to average out over any of these variants. And there seemed to be clear statistical separation between the 2 different lines. So then I asked them, okay, what are the 2 baselines you're comparing in this case? And they said, actually, these are the TRPO. They're the exact same code base, and both of them are using the best parameter configuration I have found. And so this was really puzzling to us. And I said, well, why are these lines separated? You know, maybe you didn't do enough repetition. And so when we compare algorithm and we plot these results and the zone around them, essentially the only decision we make is, you know, this n, the denominator of how many replications we're doing. And they said, well, we did 5 replications because when we looked in the literature, this is a bunch of recent papers, and we are trying to replicate the methodology from these papers, as you've taught us. Most of them are doing at most 5 repetitions. In this case, it says 3 to 9, depending on which graph. Some plots are 3, some go up to 9, but 5 seem to be about the maximum. And when they showed me this, I said, well, what does this top 2, top 3 mean? What is going on here? And they said, aha, this is the new fashion in this community, is you're going to run a whole bunch of experiments. So train your system many times, but then only report the best runs, because, you know, we can optimize these things. Now, what they're doing is essentially optimizing over the random seed, right? I'm going to run 10 experiments, train my learner 10 different times so that I can average over the variance to understand the performance of this. Here's what happens when you take the top 3 out of 10. One, you get a very strong positive bias, so your results look great, much better than the baseline you're trying to beat. But 2, the variance also appears much smaller. And so by doing this, you're actually reducing the effective variance of your experimental methodology. And in this case, it was done very crudely so that it was obvious to us that something was wrong. But it's very insidious how this can happen. And in many cases, even in optimizing the choices of our different techniques and of our different design choices, we essentially come to the same effect. So this result, as well as that of other groups, has led to very, you know, horrified cries of horror from across the community. And that is, I hope, not the message you'll leave today's session with. It's not necessarily that reinforcement learning, both as a scientific discipline and as a field of research, is completely flawed. But it is time that we take stock of what our practices, and we really improve these methodological practice. And so this is really what I've been trying to push across the community for the last 2 years or so. And so to summarize, you know, I think what we want, you know, at a very high level is to be able to make fair comparisons, but in some cases, different methods you have to consider will have a different set of hyperparameters, different design choices. They may have different sensitivities to these hyperparameters. And what method is best? Is it a neural network? Is it a simple linear regression? Will depend a lot on the amount of data you have and your computation budget. And independent of knowing and understanding all of this set of different choices, you cannot make good decisions about which method to use to solve a particular problem. In a complement to this work, we actually went further into the literature and we surveyed 30 papers in reinforcement learning from 2018 to see, you know, we identified many sources of variance, and we wanted to know how good are the papers in terms of reporting thoroughly all these possible sources of variations when they describe their work. And a paper is usually the primary artifact for describing a scientific finding. So we looked at 50 papers drawn from NeurIPS, ICML, and ICLR, which are the 3 leading international conferences for our field. So all the papers we selected had experiments. That was our inclusion criteria. Most of them, but not all, used neural networks in their experiments. 90% of the papers described the hyperparameters that they were using for the algorithm they were proposing. Most of these papers propose a new algorithm, so for 90% of the case, we're actually describing the hyperparameters. Only 60% of papers similarly described the hyperparameters for the baseline. So maybe you're proposing a new technique, but you're comparing this to TRPO. So 90% of the case, you have the hyperparameter for your new technique, but in only 60% of the case did you tell me what's the parameters you used, the design choices for TRPO. We have a link to the code in 55% of papers. The method for choosing the best hyperparameter is given or described in only 20% of papers. 10% of papers do proper evaluation on a holdout test set. And in only 5% of papers do we have significant testing that is rigorously applied. And to be clear, many papers have a little shading around their lines. I've shown you some of these graphs with a little shading around the lines. Shading isn't always proper significant testing unless you define precisely what is the criteria that you're applying for significance. You would be shocked at the number of papers that give you a little shading, but they don't describe whether they're showing the variance or the confidence interval, if the confidence interval, which confidence interval that they're considering. So at this point, clearly we need just a little bit of housekeeping in this community to be able to ensure that our results, you know, going back to my initial goal, that the results that we produce, that we present to the community are reproducible and that they can be trusted to lead to robust, application. Clearly, we are not the first field to deal with this kind of problem, and when faced with this, you know, I turned my attention to other fields that may have some critical processes that are needed. Two of them, aviation and surgery, I think you will agree with me, are both dealing with critical decisions. And through the years, actually, both of these fields have taken it into their hands to design very simple tools to allow much higher degree of performance and reliability. And I am talking about the checklist. And so in aviation nowadays, no plane takes off before the pilot has gone through a checklist of a few safety items. And similarly, though it's not as widespread, in the majority of surgery departments across North America and the world, safety checklists have been implemented and have been shown in controlled experiments to significantly improve the health outcomes of the patients going into that surgery room. And so perhaps this is the concluding act of my talk for today. In late 2018, as a result of all of this work, we introduced the machine learning reproducibility checklist. Since then, it has undergone a couple variations, and what I'm showing you is the most recent version 2.0. That's available on my website if you do want to use it for any of your own work or for your own community. The checklist has 5 parts. I'm showing you 3 on this, and I'll show you the 2 others after. There's nothing earth-shattering here. This is just all common sense. But in the, you know, fast-paced world in which we operate, sometimes, you know, a good old checklist with common sense can be quite helpful in making sure that we don't take shortcuts with our methodology. So as a first step, it asks that for any models and algorithms presented, you have a description of the setting and so on. For any theoretical claims, you have a statement of the claim as accompanied by a proof. For the data set used, there's a number of criteria that we believe are necessary for the data set to be reusable by other groups. When we go down to the code, if you are sharing code, and more we're seeing a movement towards inclusion of the code along with the paper as the 2 complementary artifacts for scientific results. And so it's necessary to specify the dependencies. In some cases, you have separate training code and evaluation code, a README file that includes the results. Finally, for any experimental results you report, whether it's a table of numbers, a graph of numbers, you know, this is quite specific to machine learning, but may be useful for other areas also. The hyperparameters you considered, so you can think of that as the design decision, training and evaluation run, this measure and the statistics you're using, and of course, some description of the central tendency and so on. And so taken together, and we've had a few iterations of this checklist, we believe this is actually a good set of criteria for presenting work and reporting results. As part of this discussion with the community, I do want to highlight one thing. I started early in the talk by claiming that, you know, the infrastructure was perhaps controllable to a high degree with machine learning and computer science in general, whereas in other fields it's much less controllable. I do want to acknowledge the fact that as we move more and more towards distributed computing environment, there are cases under which we will see sources of variation coming in, even through the hardware and some of the scheduling algorithms that are controlling these distributed training systems. And so that can't be ignored either. The NeurIPS community, which is our largest community for machine learning research, as of last date, the deadline in June yielded 12,000 submitted papers. Each of these papers, both for 2019 and 2020, had to be accompanied by a completed machine learning reproducibility checklist, which is the checklist I showed you in the previous slide, is a version from 2020. There's a code submission policy that specifically clarifies under which condition people should be submitting code along with their paper. And finally, we also ran a reproducibility challenge to encourage participants, widely sort of crowdsourcing people to repeat the results of the work going on in the papers once the papers are made publicly available. If you're interested in this reproducibility program, which I chaired for NeurIPS both in 2019 and 2020, we have a report that's available on arXiv that describes all the steps we took and the findings from those steps, so an analysis of all the reproducibility checklists from 2019. This is available already if you do want to read more about it and perhaps consider using it in some of your own conference processes. Before I close, and I will open this up for question, I'm happy to take any questions from the audience this morning. I do want to perhaps leave you with one last message, which is the following. It is easy to get caught up in the machine of academic research, and in many cases feel like science is actually a more competitive sport than anything else. And I just want to close by reminding everyone that science actually should be viewed from the perspective of a collective institution, and that our goal when we engage in scientific research is really to understand and to explain. It is not necessarily to get the paper out as fast as possible and the most citation, but really to keep focused on this message of trying to deepen our understanding and deepen our ability to explain the phenomenon of the world that surrounds us. A quick thank you to all the wonderful collaborators. It's my real pleasure to be here with you today, but a lot of the work presented here was done by colleagues, in particular at McGill University, the ones shown here on the left side. So I want to acknowledge them today. Before I turn it over to you for any questions, thank you.
Thank you, Joelle. It's unfortunate that we can't hear clapping here because everybody is muted. But this was a really great talk, and I would like to just open it to the floor now and ask questions. So the first question came in over the chat from Vincenzo Massimiliano. Could you share some thoughts on reproducibility for research involving large distributed systems experiments that would run with hundreds of thousands of nodes, run with large data sets that are also property of some big companies?
Yeah, I think there's a couple, and I don't know exactly which issue you're looking at. Let me comment on two aspects of this. One aspect of this is just an acknowledgement of the fact that a lot of the research that is done in large companies with very large clusters is very hard to reproduce by everyone. You know, we've seen, I've mentioned briefly these models with, 30 billion parameters that are being trained, and perhaps, there's a handful of companies that can do this kind of training, but most researchers in university settings certainly cannot. I've been pushing a lot on these companies, and one of the reasons I've chose to work with FAIR is because they have completely an open science position, and so all the work that we do at the company is open source and shared publicly. In many cases, it's not necessary for everyone to rerun all the results, but these large efforts should be released in the form of like a trained model, not just the code to do the training, because of course, most university researcher won't be able to do the training, but the result, like what's the parameters of the neural network after the training, make that available. And usually people can do the evaluation run locally. And so that's one important consideration of what you release. It's not just the code, but the trained model can be incredibly valuable to the community. The second take on the question is, what are the factors of variation that come in when you train on these distributed systems? And I didn't represent them or capture them to the same degree. There's one point about the computing infrastructure, which is probably not detailed enough. At this stage, we haven't looked yet closely enough at what are those factors of variation. I am working with colleagues who have that expertise, and we're kind of building up that knowledge, but I don't know yet. I couldn't tell you upright, what are these other items we should put on our checklist to report and measure. But it's a very interesting question to look out for in the coming years.
Okay, good. Thanks. I think the next one, I saw the hand, Ruben Meyer raised the hand. Maybe, yes, he's unmuted.
Yeah, I hope it works and you can hear me. So thanks for that yeah, very interesting and relevant keynote speech. I have a question regarding reproducing yeah, results that were made with, say, very complex distributed systems. Often it's very hard to even install these systems, and they have very specific requirements, and you try to do it, you follow that list, it takes you a day or longer, it crashes, you don't know, and the authors also don't want to offer support, of course, for they have even more work, right? They publish their code and then they get a lot of support requests which they don't want to do. Is there any solution to that, like also offering a simple implementation that that is easy to run, just say run make and then it and then it really works, something in that direction? What is your opinion on that problem?
I think this problem is very real. It's one my students certainly have experienced, as well as colleagues. On the one hand, I think, you know, I'll reiterate what I said a little bit previously, which is I don't think we've yet documented all the subtle pieces that are needed to really ensure reproducibility for some of these more complex systems. And so I would, you know, kind of stay tuned for more on that in coming months or years. The other piece I will add is I didn't have time to say much about the reproducibility challenge, but the reproducibility challenge essentially called on the community to take a paper submitted. We had one with NeurIPS, we had a previous one with iClear. You take a paper and you try to re-implement it yourself, and then you write a reproducibility report, and that report is publicly available. In our case, we use the platform Open Review to share all the reproducibility reports. And so what happens if someone did that, spend a day or two trying to do that and failed in many different ways, they can at least document that, produce that report in the community so that if other people want to use the same code, they will be warned about all the difficulties that previous people experimented. Sometimes the difficulties come further down the line. You kind of know how far you can get and where you're going to hit a snag. And so these reproducibility report actually a valuable contribution for the community so that, you know, you can never publish these negative results, but at least now we have a repository of them. And we've been using these reproducibility challenge as course projects for some of the graduate course. It makes a very nice course project. And both there's a contribution to the community as well as a learning experience for some of the junior researchers and just joining the community.
Thank you very much.
So the next question comes from Valerio and is on the chat. Some results cannot be reproduced, I'd say by design, due to the private confidential nature of the data being managed. Any thoughts on that?
That's absolutely right. And thank you for pointing it up, especially, you know, a lot of the work that we do with medical data, when it's, you know, the kind of animal model of epilepsy, that's fine, we can release the data. But when you're actually, and more recently, we have a project partnership with Montreal Hospital with COVID patients, and we're getting clinical data and scans from COVID patients. Clearly, if we do find a good algorithm, we won't be able to release the data sets for that. I think, you know, everyone has to adapt to this. For many of the work we've done with medical data, we can still release the code, we just can't release the data set. And so the burden of reproducibility, there are trade-offs there between transparency and between privacy. And on each case, you have to appropriately judge where to draw the line. This is one of the reasons why some of the conferences, including NeurIPS and ICML, were toying with the idea of having a mandatory code submission policy, data submission policy. And one of the reasons they stayed away from making it mandatory is an acknowledgement that there can be nuanced reasons why someone cannot provide those artifacts, and we want to be respectful of that. An interesting thing we've seen is even though we didn't make it mandatory, the number of people submitting code has increased very quickly. 2018, we had 50% of papers accompanied by code. 2019, we were at 75% of papers. 2020, I don't have the results yet, but this is a huge increase. And when we think that we're looking at like 12,000 papers, going from 50% to 75% is a huge step in terms of, you know, voluntary participation in submitting code with your results. So yes, absolutely, transparency versus privacy. You have to be careful how you thread that and discuss with your collaborators how to handle that.
Okay, The next question is from Tim Brecht. If you are able to replicate or reproduce results from a previous paper, is that something then can be published in your area? I believe that a fundamental problem is that in many areas such results are not publishable, which is fundamentally different from many fields of science. This discourages people in areas of CS from doing such work because it will only be publishable if you're not able to reproduce. If you're not able, you're able to publish, but otherwise not.
Yeah, thank you for asking that. I didn't have time to get into this, but if you look into the archive report I shared with the results of the NeurIPS 2019 reproducibility program, what you will see is that for the participants in the reproducibility challenge, each of which produced a reproducibility report, we actually partnered with a journal. There's a journal called Rescience. It's not a journal that's specific to AI and machine learning, so it could be open to other communities. The journal Rescience specializes in producing reproducibility studies, so we did a special issue of that journal. We did one in 2019, we did another one in 2020. So of all the reproducibility report, we sent them for review by the original NeurIPS paper reviewers. They gave back, and we picked a set of 6 or so reproducibility reports that we thought were of the highest quality, and we published them in that journal. It's an online journal. You can have access to the papers if you're interested, and it gives examples to the community of what a good reproducibility report looks like, and it counts as a citation for the authors.
So, and this was also positive results when you were able?
When we were or when we were not. And usually, I should be clear, reproducibility, it's never a yes or no answer. It's never like, yes, absolutely, or no, not at all. It's always much more nuanced. There's some things we can do. There's some things you don't get quite the same thing.
Okay. So the questions are coming in. I know you have a sharp deadline there, Sarah. We'll see how far we get. Kai Wen asked, could you comment on the relative impact of factors affecting reproducibility in the techniques you studied? Is it the non-determinism in the algorithms themselves, race conditions, multi-threaded execution, variance in hardware, variance in the input data? What is it?
I would say foremost for machine learning and deep learning, it's the choice of hyperparameters and the method chosen to optimize, to select the hyperparameters. Those are the 2 big ones. The third big one is the choice of the data. Now, in a lot of papers, you don't see that because everyone's using the canonical data sets like ImageNet or these kinds of data sets. So as long as everyone's using the same, it's exactly the same. But if you were to go back and get images that are not from ImageNet, like just new images, the data set collection would be a huge source of variation. So it's much less the thing we think of in terms of the underlying machines used to compute it. It's much more the humans. Whenever the human is making decision, that's what's injecting a lot of the variance right now.
Okay, great. I think it's actually, this was the last question because there were obviously comments. Other communities have been working on this too. And ACM, obviously it's very specialized for every field. So it was very interesting to see what is going on in your field and what are also your problems. I mean, we are systems people, so we know and we struggle by ourselves just in a very similar way. So you saw a lot of people were asking about hardware because that is a big struggle for us. Certain configuration parameters are also a struggle. So it was really great to hear. What I would like to do before people give you a final applause, I would like to quickly share my screen and the name of, do you see this? Or do you
Yes.
Yes.
I see it.
In the name of the organizing committee, you get a gift. I must admit, I asked Aaron what you might like, and he said you like experiences more than material things. So we got you a gift certificate for a repair, Pharaoh's restaurant. I checked it, it's open. It starts the full service only end of August. It has kind of right now a special deal, but its full-fledged things will be open end of August, we all hope. And so here are kind of a gift certificate that you can enjoy. Obviously you can go with whom you want to go, but you know that Aaron knows about it. So I'm just giving you the hint. With that, I'll wanted to stop the sharing again. And
thank you so much.
finished the session exactly on time, and I think everybody will be happy to give you a great applause for this very, very excellent and informative talk. Thanks so much.
Thank you for the warm welcome. It was a pleasure to be here with you this morning.
Thank you, Joelle.
Great. Kai Wen, maybe you want to quickly just say how things are